So, welcome to our first flipped classroom video lecture of the year, where we are talking about scientific thinking. So, first thing we're going to talk about is just a quick review of the scientific method. You guys have been learning about the scientific method probably since second grade. So this should all be a review, but there are a few things that I want to point out that we want to make sure that you have a little bit more sophisticated understanding of going into chemistry. So first, what is the scientific method? So when we talk about the scientific method, we're really just talking about this logical, stepwise approach that scientists use to find answers to questions, to solve problems. So we said it's stepwise. We're going to talk about the steps of the method. It's really important to understand that scientists are always refining their understanding. And so when we answer a question or solve a problem using the scientific method, once we reach a conclusion, we frequently loop back around to the top. So it's really important to not think of this as a linear process, but really as more of a cycle with constant iteration and constant refinement. That said, we have to start somewhere. So let's say that we're going to start with observations. So observations are things that we can see, things that we can hear, things that we can taste or smell or measure. So observations can be quantitative, they can be qualitative. Quantitative means that we can associate a number with it. That's usually a measurement. Qualitative means that it has more to do with simply things that we can observe using our senses. So that might be smell, that might be color, taste, although we're never going to taste in the chemistry lab. So any of those measurements that we make with our senses would be observations that are more qualitative than quantitative. So once we make those observations, then we can start to ask some questions. Those questions frequently are a problem that needs to be solved, and those questions come from those observations. So if I were to say, notice that my aloe plant looks slightly wilted, that would be the fact that it is wilted is an observation. My question might be, why is my aloe plant wilted? So I'm going to conduct some background research. Now, in the case of the aloe plant, probably not a whole lot of research needed there. But when we get into more sophisticated and more difficult problems, we're going to do background research. We're going to consult journals. We're going to consult our peers. We're going to look at textbooks. Google is not research. It is a tool that we can use for research, but we want to make sure that we are consulting actual journals and periodicals. So once we've done some research, we've made some observations, we can probably make an educated prediction of what will happen based on that research, maybe based on our prior knowledge. So in my case of my wilted aloe plant, I might say that if I water the aloe plant, then it will stop being so wilted. It'll absorb the water through its root system and it will turn green and regain its form. Now, of course, we need to test. We need to design and perform an experiment. It's really important when we test that our test is reproducible. So we are always going to create a procedure in order for another scientist to be able to perform the exact same experiment in the exact same way. If we can't do that, we're not doing good science. As we test, of course, we're going to gather data. That might be quantitative, again, numerical measurements, or it might be qualitative. I might notice that today the plant looks greener. I might be able to measure growth. I may be able to say that it added 5 millimeters in the course of a week. And once we've gathered all of that data, we're going to do some analysis, and then we're going to form a conclusion about our experiment. We are going to think about, was our hypothesis correct? Should our experiment be modified and repeated? Okay, that repeated process is really, really important. So in the case of my aloe plant example, I might find that although it became less wilted, it's still not very green. And so I might consider repeating my test and changing something up, adding fertilizer, changing the soil. So we're always going to continue to refine our results. So that's our steps of the scientific method. Remembering, of course, that the scientific method is not a straight line, but in fact is a cycle. We're going to make that observation. We're going to come up with a hypothesis. We're going to test our hypothesis. If our hypothesis fails, we're going to come up with a new hypothesis and we're going to test it again. If it passes, we're going to keep testing it. If it passes after being tested many, 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 many times, it can become what we call a scientific theory. We will continue to test that theory. If that theory then fails, we're going to go back to the top and we're going to test again. It's really important to understand that a theory never becomes a law. Okay, a scientific law is one that is simply accumulated observations. So it is something that is provable. Okay, the law of gravity says that if I were to take an object and lift it up and let go of it, it's going to fall. That's the law of gravity. That can be tested. It can be proven. The theory of gravity says that the reason that it falls is that the mass of the Earth attracts the mass of the object. That's a theory. It attempts to explain the observation. So a theory is an explanation, an observation is simply a what. So it's important to recognize that those two things are related, but a theory never becomes a law because a theory explains why. Okay, so one of the hardest things in science is writing a good conclusion. So we're going to work with this kind of framework that I think you guys have been introduced to already, called claim evidence reasoning, or CER. So we've gathered all of this evidence through our experimentation, and now we're going to make a claim. We're going to write a conclusion. We're going to answer our question, and we're going to use our scientific reasoning to connect our evidence to our claim. So the claim is the conclusion. It answers our question. It's one sentence. It shouldn't have anything like a because. Okay, so if we go back to our aloe plant, my claim would be that increasing the amount of water that I give to the aloe plant made it less wilted. That's it. Okay, that's my claim. Now, evidence. Evidence is data that supports our claim. This might be quantitative or it might be qualitative. You want to make sure that you have appropriate data. We want to make sure that we have sufficient data to support our claim, and it should directly support our claim. So these are these observations, quantitative or qualitative. And then our reasoning explains how our data supports our claim. We're explaining how that evidence can be interpreted. And so if we go to our example of the aloe plant, what do I know? I know that adding water to the aloe plant made it less wilted. How do I know? Over the course of 3 weeks, I observed my aloe plant every day and saw that the wrinkles in the surface of the plant disappeared. Plant became more green. How does my evidence support the claim? Well, I remember from my biology class that plant cells have cell walls. And so when there's enough water inside the plant cell, it expands the cell, and that's what causes those wrinkles to go away. And that's how I know that water is what caused the difference that I saw in my plant. Okay, so we'll watch a video in class to go through this process again. As always, if you have any questions, please write them down. Let me know. We'll talk about it at the beginning of class. Look forward to seeing you.